This section presents the fundamental theorem of calculus. But we want to review what we went over in the last section. Recall the use of Riemann sums, and that is where we were looking at the area of a region bounded by two vertical lines, a function, and the x-axis. And the way that we found that region was to draw some rectangles, some representative rectangles, and add up that area. Well, what would happen if we had an infinite number of rectangles? In the previous section, we looked at when we used more and more rectangles, we got a closer and closer exact answer. So if I just keep dividing up these rectangles and saying and taking the area, and then I split them in half and split them in half until the limit of delta x, and remember delta x is the width, approaches 0, we're going to get an exact value. And that leads us to this definition that the area of the graph, if it's a non-negative, meaning it's above the x-axis, then the area is the limit as n being the number of rectangles, approaches infinity. And the way that would approach infinity is that delta x would approach 0. That's going to give the area underneath the graph. So again, we have an infinite amount of rectangles. That gives us the definition of the definite integral. So we have a function defined on a closed interval from a to b, the limit as n approaches infinity, and remember n is the number of rectangles, and we add up all that sum, where remember delta x is the width, then we get the area underneath that graph. And so we are introduced to this notation right here, which is the integral sign, and we're going to find the integral, which is going to give us the area bounded by a curve. Notice we have an a, which is the lower limit, which is that first vertical line. B is the upper limit, which is that second vertical line. We don't have to just have functions that are above the x-axis. We can also have functions that dip below. Now what's kind of interesting here is this would be positive area above the x-axis, where this would be actually considered negative area, which is kind of an interesting concept since you've been probably taught since day one area, length, width, and all of that needs to be positive. But just because of the graphical representation, we can sometimes look at that as a negative area. And so this definite integral from a to b gives us the geometric representation. So if we were to add these regions, meaning that R1, but we would subtract R2 plus R3, would give us the area bounded by f of x between the vertical lines of a and b. And that is the fundamental theorem of calculus. That if we have f is continuous, remember that from the very first chapters, that we don't have any leaps or holes or asymptotes on a closed interval from a to b, then we can evaluate that f of b minus f of a. Notice we have our upper minus the lower, where f is that antiderivative that we talked about and defined on previous sections. So let's look at how that's going to play out. Find the area of the region under the graph on the interval between -1 and 3. The previous section we actually drew this. This would be a line, and we would get a triangle, and we could find the area that way. But let's see what the calculus goes. So we have this integral sign, that elongated s. We have a lower limit and a higher limit, so we have this is a and this is b. So from -1 to 3. Then we have our function -2x plus 4 dx. So now we're going to use our integral properties that again we learned about a constant and the power rule. But this time we don't have that plus c. That plus c was the indefinite integral. Now we have the definite integral. So let's see if we can remember how to integrate this. Well, remember we can pull out the constant, and then this is the power rule. So we add 1 to the power and then divide by that new power. 4 is just a constant, and remember we just put an x on that. And then we're going to evaluate that between -1 and 3. That's an interesting notation. That's just what that means. So we're going to now plug in 3 for x. So that would be that f of b. So before I do that, let's just clean that up. Those 2's would cancel. So I would have negative x squared plus 4x evaluated between negative 1 and 3. So we would have, we would have negative 3 squared plus 4 times 3. That's putting the upper limit. Then we want to subtract the lower limit. And my best suggestion would be to make sure that you put the upper limit in some kind of parentheses or brackets and the lower limit in some kind of parentheses or brackets, and you don't lose that minus sign. Right, so let's do the arithmetic. So that's negative 9 plus 12. That would be negative 1 minus 4. So we have 3 minus a negative 5, 8. And so the area underneath this graph would be 8 square units. Okay, so we know that the area is 8 square units, but let's just look at a graph. If we were to graph that, that's a line where b is 4 and the slope is 2. So down 2 over 1, down 2 over 1, down 2 over 1, that kind of thing. All right, and so if I bound it by negative 1 and positive 3, we would have the area of this triangle above and this triangle below. Let's just see if we can do some geometry. So this is 1, 2, that's 3 units. 1, 2, 3, 4, 5, 6. I believe when x is negative 1, y would be 6. All right, so this would be 3 times 6 is 18 divided by 2. That would be 9 square units for that triangle. All right, then we have this one. That's 1, that's 2. Base times height divided by 2. That's an area of 1, but remember it's below, so we would subtract that. And lo and behold, 9 minus 1 is 8 square units. So the calculus really does work. All right, so now let's look at this next example. We have a parabola, a quadratic, that's going to be upside down. Not need to graph it, but it is going to be, we're going to find the area underneath the graph between 0 and 4. We set up our integral for 0 to 4. So again, we're just going to be using the power rule. So on here, we keep the constant out in front, add 1 to the power, and divide by that power. Power rule again, so add 1 and divide. And here's our function, and I'm going to evaluate that between 0 and 4. Let's again reduce. So I have 2x squared minus x cubed over 3 between 0 and 4. So that's 2 times 4 squared minus 4 cubed minus 2 times 0 minus 0 over 3. It's always nice to have 0 as a limit. Usually the math is really easy because you can see all of that is 0. So my area is going to be 16 times 2, that's 32, minus 64 thirds, and that would be 32 thirds of square units. Again, you could go back and look at the graph of that and kind of compare, but since we don't have a formula, we really couldn't get an exact answer like that. We could use Riemann sums, but the calculus gives us that exact area. All right, so now we've got that e. Oh, joy. All right, so we've got our integral between 1 and 2 of e to the x minus x dx. That just tells us what variable we're integrating with respect to. So let's see, what's the integral of e to the x? That's just e to the x. The integral of x is x squared over 2, and then I want to evaluate that between 1 and 2. So I have e squared minus 4 over 2 minus e to the first minus 1/2. All right, let's just leave the e's as e's for right now. Don't forget to distribute this minus sign. That's a very common mistake. All right, so I have e squared minus e, a negative 2 plus 1/2 is a negative 3/2. We could leave it like that, or you could go to your calculator and get a decimal approximation. This is approximately 3.17. All right, so now your homework's going to switch. Instead of saying finding the area of the graph and writing it like this and giving you the function, it's just going to say evaluate the definite integral, and they're just going to give you this. All right, same idea. You're still finding the area under the graph. just kind of skipping those long words and putting them in a shortcut form. So let's work that problem. We have 1 to 2, 2 over x dx. A lot of students kind of forget this one. If I pull out the 2, you can't rewrite that as x to the negative 1 and use the power rule, because then you would divide by 0. That is not the power rule. This is the natural log rule. And remember, it's the absolute value. And we don't need to put plus c because we have a definite integral. So it's going to be 2 times the natural log of 2 minus 2 times the natural log of 1. We could drop the absolute value signs because the absolute value of 2 is 2. But hopefully you will recall or check on your calculator that the natural log of 1 is 0. So 2 times 0, that's all 0. So this would be an acceptable answer. However, just to kind of throw this in, you could move this up here and say this is the same thing as the natural log of 4, because 2 squared is 4. That would be your exact answer. That's what I would prefer. You could check it out on the calculator as well. All right, so now we just have evaluate, but that still means to find the area of the curve bounded by 1 and 4 on the x-axis. So anytime you see a radical, we need to rewrite that as an exponent, so that's the 1/3 power. So I can use the power rule. Now remember, the power rule says you add 1 to the power, so that's going to be 4/3, and then you would divide by that, which means multiply by the reciprocal. So that's going to be x to the 4/3 multiplied by 3/4. So that's 3. That's the cube root of 4 raised to the 4th power over 4 minus 3 times the cube root of 1 raised to the 4th power over 4. Let's do the easy part first. Cube root of 1 is 1 to the 4th power. That's still 1, so that's just minus 3/4. But what the heck is this? Well, we could get a decimal. All right, but let's look at that. 4 to the 4th power. That's 4 times 4 times 4 times 4. And I want to take the cube root of that, because just remember, you can put that power on the outside or you can move it on the inside. It's kind of your choice. So that's still the cube root. So a cube root, you want 3 of a kind. So this would be 3 times 4 times the cube root of 4 over 4. So that would be your exact answer. That is a 4 right there. You could also do a decimal approximation, but I'm looking for exact answers on the next test. So let's see what happens here. We've got a negative to a positive. All right, not a big deal. So we've got but we've got a power here. What can we do? Do I need to use substitution? What's going on here? I could square that out, but let's see if I could use substitution. If I let u be x squared minus 1, then du is 2x dx, and I don't have an x, and I can't put that in. All right, so I can't use u substitution. So that means I must need to FOIL this out, multiply it out. That's much easier. Then I can just use the power rule. Okay, so I'm going to plug in 1, so I have 1/5. That's 2/3. Well, I don't want to confuse you. Let me write it like this. So that's 2 times 1/3 plus 1. Then we have negative 1 to the 5th power is negative 1/5. Negative 1 to the cube is again negative 1. And then we have just negative 1. Now notice there's lots of negatives. Let's be careful. Negative, negative, that's going to be plus. This negative and this negative, that's a positive, but this negative here is going to make that negative 2/3. And then this negative and this negative is plus 1. Do you have anything that cancels? That's a third. No, they're all alike. So let's see. 1 plus 1 is 2. 1/5 and 1/5 is 2/5. Minus 2/3 and minus 2/3 is minus 4/3. All right, so we could find a common denominator, which would be 15. So that would be 30/15 for the 2 over 1 plus 6/15 for the 2/5 minus 20/15 for the negative. So let's see, 36 minus 20 is 16/15. Go back to your basics, do your fractions, don't panic. Ooh, that looks ugly. I can't just distribute this because of that. Let's see if I could use u substitution. Let's see, if u is the square root of x plus the square root of 2, and that's just a constant, so I'm not going to worry about that, and I take the derivative, That's going to be x to the negative 1/2, and that's going to be 0. And I don't have this here, so I don't think they mean for me to use u substitution. Let's go ahead and multiply it out like I did before. So I have to FOIL that out. All right, so we need to go back to basic algebra. I need to write that out twice. So I get x plus 2 square roots of 2x, because those are like terms, plus 2. And then I'm going to distribute, so I have x square root of 2x. Now, square root of 2x times the square root of 2x is just 2x times that 2, that's going to be 4x. And I distribute here. Wow, that's kind of ugly. What am I going to do with this and this? How about let's get rid of those square roots. So this is x times 2x to the 1/2 power. This is 2 times 2x to the 1/2 power. Okay, then, remember that's 1. This half is going to go to both of those, so I can add those exponents here. So I'm going to have this square, the 2 to the 1/2 power, and then x is going to be to the 3/2 power, 1 plus 1/2. And here I can't multiply 2 times 2 because that's not what that is. That is going to be, let's see, that's really the square root of 2. So I'm going to have 2 square roots of 2 and then x to the 1/2. And yes, that's ugly, but I really need those exponents to do the calculus so I can use the power rule. Actually, I think I can integrate now. Let's go back and look. That's just a constant. Remember, 2 to the 1/2 is the same as the square root of 2. So I'm going to have the square root of 2, and then integrate here, add 1, that's going to be x to the 5/2, and then divide by that, or multiply by the reciprocal, which would be 2/5. Add 1, divide by that. And now we've got an x to the 1/2, so we add 1 to that, that's x to the 3/2, that's multiplied by 2/3. Ooh, that is ugly. Thank goodness we have a 0 as a lower limit. Alright, so let's see. We've got 2 square roots of 2/5. Those are all the constants. Then I've got x to the 5/2 power. So that's 1 to the 5/2 power. Okay, then that's going to reduce. So that's 2. Then that's 1 squared. So I've got this 2 and that 2. So I've got 4 square roots of 2 over 3. And then I've got my variable 1 to the 3/2 power. So I have all of that minus, and then hopefully you can see if I put in 0, the same place I put in those 1s, what am I going to do? I'm going to get a big fat 0. Alright, so I have 2 square roots of 2 over 5 plus 2 plus 4 square roots of 2 over 3, and that is ugly, but that's what we're going to leave it as. That's a very complicated problem, a lot of exponent rules, but the calculus is actually easy. Alright, so you're going to get to some word problems at the end. So let's read this for a minute. So we've got that marginal cost function, and remember that's the derivative. So we want the total cost. So if they give us the derivative of that, then we need to go backwards. We need to find that antiderivative. And the antiderivative would be, remember that integral. So I'm going to take the integral of this function, and I'm going to work with the indefinite integral right now. Don't forget put that plus c since this is an indefinite integral. Okay, so I'm going to just reduce this and that. Okay, so part A says find the, oh wait, let's go back. So I want to, management has also determined that the daily fixed cost is $800. And I want to find the total cost in producing the first 300 units. So this fixed cost right there is saying that if I have my cost function, which is what I have here, and if I let x be 0, meaning I have not done anything, if I put in 0 here, here, and here, that's all going to be 0, I would get C. Well, but this is saying that if I don't produce or make anything, I still have a cost of 800. So that concludes that this constant is going to be that $800. So now I can find the total cost because my cost function is this, that 800 goes in at the end, and now I just need to evaluate this function for 300. So I'm going to go through and I'm going to put a 300 everywhere there is an x and definitely use a calculator. So my cost to make 300 units of toaster ovens per day is $4,100. Alright, so as we look at the cell phone, it says cell phone advertising spending is expected to grow at the rate given by this. And it's bounded between 1 and 5 years. Part A asks us to find an expression giving the cell phone ad spending in year T. So if it's growing, if you remember, that would be like dr dt. That would be at a rate. I want to know what I would spend. Okay, so if my spending rate, I need to go backwards. I need to take the integral. So I'm going to take the integral of this function here with respect to the variable t. So I'm going to pull out this constant, and remember I'm going to add 1 to this, so that's t to the 0.96, and then divide by that new variable, that new exponent, and then I'm going to take my calculator and divide those two numbers. Comes out kind of nice. I have 0.086 t to the 0.96 plus c, and that's going to be my ad spending in year t, so I'm just going to call it a of t for ad. Alright, now notice in year 1, which was 2007, I spent 0.9 billion. So I've got to solve for that constant. Alright, so let's see, when t is 1, I've solved 9 billion. So a of 1, what's t? T is 1, so I'd have 1 to the 0.96 power plus c, but what does that equal to? 0.9 billion. So since the function was given in $1 billion a year, I'm not going to put all those zeros. So I have 0.9 equals 0.086. 1 raised to any power is 1. Solve for that constant, and that's going to be 0.04. So what that tells you is that your function for ad spending is equal to 0.86t raised to the 0.96 power plus no longer a constant, but 0.4. Now, if the trend continues, what will be the cell phone spending in 2012? Well, remember, when t is 1, that corresponds to the year of 2007. So what is t 2012? Really just count on your fingers. 8, 9, 10, 11, 12. So t is going to be 6. Now you want to substitute in 6 for t, 0.86 times 6 raised to the 0.96 plus 0.4. Now you want to grab a calculator, and that's going to be approximately 5.2, and remember this was in billions of dollars. So just to tell you what those last two word problems are, is that we are really solving what's called initial value problems. We're taking that antiderivative and getting that family of functions with that indefinite integral of plus c, and we're taking some initial value conditions to solve for that constant of c. So this whole lesson, that fundamental theorem of calculus, is just defining what an integral is, how to use all the properties that we've learned in the previous sections, and just putting all of those rules and integration techniques together.